Lecture 2. Starting off with Chapter 4 here. Lecture 2 is going to be the first half of Chapter 4. Lecture 3 is going to be the second half from 4.5 onwards. Still going quite fast through material to try and catch up to diodes in order to have you guys prepared for lab number 1. After that, it's going to get a little bit more relaxed of a pace. Intro to nonlinear circuit elements. 4.1 Water analogy for diodes. The most basic nonlinear circuit element is a diode. A diode's basically like a one-way door in a water pipe. So here's the water pipe. You can see water can go in here, but if it tries to travel the other way from right to left, then it'll be blocked by the door. Similarly, a diode allows current to travel easily from left to right in the direction of the arrow, but not so easily from right to left. Bands and band gaps. This material may be a little bit of review for you if you've done some 3FO3 stuff. If not, then it's just going to be a cursory overview. We're not going to get too deep into it for this course. Infinite potential and square wells. To understand the behavior of electrons, we have to use the time-independent Schrödinger equation, like this. In semiconductors, we can visualize the electrons as particles in a square potential. So here's our square potential. You may have solved this before. You get a number of energy states which kind of look like the energy that you'd have on a string for vibrating energy. We've got like a node on the left and a node on the right, and the different wave functions that fit in between. If we have a lot of square wells and we want to couple them together, so let's suppose we just start off with 2. If there's an infinite barrier height between them, then they don't interact with each other. But if there's a finite barrier height, then there's 2 important ways they can interact: the symmetric solution and the anti-symmetric solution. This symmetric solution turns out to have a little bit lower energy than the anti-symmetric solution. One way to see that is this kind of looks like it's almost like double the wavelength. Despite the little bump in the middle, it's more or less like it's got half the frequency of this one, which has to flip from left to right. Higher frequency things are higher energy, so that means this one has lower energy associated with it. If we've got a bunch of wells together, say in a semiconductor, we create a number of bonding and anti-bonding states. The bonding states being the ones that have this symmetric coupling, and anti-bonding being the ones with anti-symmetric coupling. Bonding energy states being a little bit lower energy than the anti-bonding ones. Important materials that we're going to be concerned with are insulators, semiconductors, metals, and then there's also semi-metals, but we're not going to worry about that. So semiconductors and metals, the big difference is where the states are filled to. In a semiconductor, there's a band gap between the energy states that are filled and the energy states that aren't filled. So up here, there's a lot of energy states, but there's no charge carriers, or a very small amount. There's some kind of a gap called the energy gap between where the charge carriers are and where they need to be for them to conduct. In an insulator, we've got the same situation, but the band gap is very wide. So in a semiconductor at room temperature, you may have thermal excitations prompting some electrons from here, called the valence band, up here to the conduction band, where they can then move under the influence of an electric field. A metal, there's no gap. So in a metal, there's no gap between the top of what you might call the valence band and the bottom of the conduction band. The states are right next to each other, so electrons can very easily move, even at low temperatures, left and right. In semiconductors, we distinguish between a direct gap and an indirect gap. Direct gap is one where electrons can go from the valence band to the conduction band without having to have a momentum transfer. In an indirect gap material, the band shape is such that the lowest energy in the conduction band is actually at a different wave number, a different momentum than the top of the conduction band. So the most efficient energy-wise way to transfer from one band to another requires a momentum transfer, so you can't actually jump from valence to conduction band without involving a phonon. If an electron leaves the valence band, it leaves behind a spot where they're is a state for an electron, but there isn't an electron. This allows the neighboring electrons to move into that spot. So if we go back up to this picture, you can see now there's an empty spot. So you might have this electron jump into that, then the next one can jump, then the next one can jump, then the next one can jump. So this gap of an electron, which we're going to call a hole, behaves almost like a positive charge carrier moving around. And so in semiconductors, you'd often keep track of holes as well as electrons and consider that. Semiconductor doping. The way to get a lot of charge carriers into semiconductors is to insert impurities into a semiconductor. The type of impurity that you'd want to insert, so instead of, let's suppose we've got silicon, it normally has 4 spots. If we were to take an element like nitrogen and put it in there in the place of a silicon, this has 5 valence electrons. So that means that there's 1 extra electron that doesn't really have anywhere to go in the orbitals. So it behaves kind of like a free electron. It very easily is able to jump into the conduction band and move around and be a conduction electron. You can also get a free hole by, instead of inserting an element that has too many electrons like nitrogen, you can insert a group 3 element, say like boron. Boron has 3 electrons in its valence band. So unlike the silicon with 4, it's missing an electron, and this creates a free hole that behaves like a positive charge carrier. In other words, it's very easy for an electron from the valence band, one of these ones that's normally locked up in the bonding, to jump into this empty spot here. Looking at the band energy picture, we've got conduction band up here. There's very few electrons in there, but if there are some electrons there, because there's a lot of empty states to move into, they can move back and forth in there under the application of an electric field easily. In the valence band, there's not many states that are empty, and but if we were to make an empty state, then all the other electrons could move into that, and so it's like the state could move around. This is where holes exist, and this is where conduction electrons exist. A lot of the time in semiconductors, you'll just refer to electrons and holes, and usually by saying electrons, you mean conduction band electrons. I'll try to specify conduction band electrons when it could get confusing. Holes, you're only concerned with down here in the valence band. Okay, so a donor atom or donor impurity in silicon, that would be something that has an extra electron that it can donate, say like our nitrogen example, creates an extra energy state that's up here. It doesn't take much thermal energy to empty this energy state out and promote an electron up to the conduction band. Similarly, an acceptor impurity like boron has this energy state that's very close to the valence band, allowing an electron from there to jump up into it quite easily. So here's just an understanding to try to review this. Nitrogen, chemical symbol N, is an N-type dopant in silicon. What type of dopant is phosphorus, chemical symbol P? If you said P-type dopant, you are wrong. Phosphorus lies below nitrogen, so it is also an N-type dopant. Moving back up a little bit, one thing that we kind of glossed over is the energy function in the conduction band. So the energy in the conduction band is going to depend on the momentum of the electron. So it's going to depend on its wave number, k. We can get a picture of what the energy looks like as a function of k through this equation. Energy is basically the energy for k equals k naught, but modified by how different the momentum is there, different the momentum is at every point. So this basically creates an effective mass for the electrons there, given by h bar squared over the partial derivative of E with respect to the wave number. Suppose that an electron band is given by E at k is negative a cos Ka, where a is the lattice constant of the material, the spacing between the cells, and a is a constant. What's the effective mass of the electron near k equals 0 in this case? What's the effective mass if a is 5 angstroms and a, big A, is 0.5 electron volts? See if you can use that formula. Practice some derivatives. All right, giving it a shot, you can use the small angle approximation of cos and come up with this Or, taking the partial derivatives, you can find that formula for the effective mass. Substituting in the values we're given, we find the effective mass is 4.6 times 10 to the negative 31 kilograms. What this means is because of the shape of the conduction band, electrons will behave more like they've got this mass than their actual mass. 4.4, interfaces and band bending. If we actually want to use a semiconductor in some kind of circuit, we're going to need to connect it to conductors, so our wires. This creates a junction. A junction between two different types of material is a heterojunction. A junction between the same type of material would be considered a homojunction. Metal-to-metal junctions. Remember that the work function is the energy needed to remove an electron from a metal. Now, the Fermi energy level, is the energy level of the last filled state at absolute zero, or halfway between that state and the first unfilled state, if you want to be very technical about it. The Fermi level in a metal then tells you about how big the work function is. So when two metals are connected, the potential energy, electrons are going to move such that it creates an electric potential difference across the junction. So we remember from previously that the metal with the lower work function is going to have electrons transfer from it over to the metal with a higher work function because they see a larger, they basically drop to a lower potential energy when they jump over there. So electrons are going to transfer until the Fermi levels are matched in the two metals. This lineup of the Fermi levels means that the potential energy potential energy relative to vacuum difference in the two metals, now that the Fermi levels have lined up, means that an electron on the right-hand side is going to need more energy to be ejected than an electron on the left-hand side of this boundary. So the energy level of a vacuum seems to have bent. This happens for all of the energy levels inside from before. So if vacuum was our reference point for the same energy everywhere, then we have kind of straight energy bands across in position. But now that we've connected these two metals, all the energy levels, including the vacuum one, have kind of bent from left to right so that the Fermi levels are lined up. We can figure out how the bands bend using the Poisson equation by assuming that the motion of these electrons creates a region on one side, which is a certain thickness d, where we are depleted of electrons, and a region on the other side where there's an increased number of electrons, which is the same thickness, and we'll say that they're uniform density of missing electrons creating positive charge on the left and extra electrons creating negative charge on the right. Solving the Poisson equation in this charge region gives us the following potential. Now, by asserting that the boundary is continuous, that the potential doesn't jump at any point across this junction, we can calculate how big this distance is, this distance of of missing electrons and extra electrons that has a bend in the energy band. So how big is this really for a metal? Substituting into our numbers here, we find that it's only actually a few angstroms for a metal, so the potential energy is nearly uniform everywhere except at the contact surface where there's this contact potential created by the difference in work functions. Doped semiconductor interfaces, PN junctions. All right, a PN junction, the basis for many semiconductor devices, is just an N-type semiconductor connected to a P-type semiconductor. The connection of them is called the junction. This does some pretty interesting things. So here's our N-type semiconductor. It's got all these extra conduction electrons due to the donor atoms that are inside there. And here's our P-type semiconductor. It's got all these extra holes compared to a neutral or an undoped semiconductor due to the extra acceptor impurities. Now, in between, what happens is these electrons combine with the holes over there to eliminate each other, and we have this depletion region which has very few charge carriers compared to either of the sides. So because of these extra charge carriers, this is a good conductor, this is a good conductor. The depletion region is a little bit more complicated. Let's look at what happens when the Fermi levels are connected together. So we've got on our N-doped material on the left side. We're going to stick with N-doped on the left and P-doped on the right. So N-doped on the left has this donor state that's higher energy, really close to the conduction band, and the acceptor state on the right-hand side, not filled with electrons, is really close to the valence band. The first picture is what it looks like at absolute zero, and so that's why there's nothing filled here in this acceptor energy band. At a very slight temperature above this, we'd find some electrons filled in the conduction band on the donor side, and the electrons filling up the acceptor band, creating holes on the p-doped side. When we connect them, still the Fermi levels line up. Since we had this raised Fermi level on the left and relative to the Fermi level on the right, for the Fermi levels to line up, we've got to have some pretty intense band bending between the N-doped and the P-doped semiconductors. This does some interesting things that allows charge to transfer from left to right and right to left. So let's look at how some of those charge carriers can move. On the left-hand side, since most of the charge carriers are electrons, we call that the majority charge carrier. On the right-hand side, the majority charge carrier is holes, because there's an extra abundance of holes there. Now, the electrons on the left-hand side, there's a couple of ways they could get over here onto the right-hand side. One way is that they could just tunnel through this energy barrier. So there's some spots over here. Maybe they could jump into one of these acceptor states, or they could jump into the valence band states over here and recombine with a hole. It turns out that that's kind of difficult to do, because there's not a whole lot of states over there that are available compared to the vast number of conduction band states up here. So an easier way is for them to just have enough energy so that, you know, this is their kind of potential energy, but their kinetic energy might be higher if they're moving around really fast. So imagine there's some heat involved. Then they may be able to just jump across this barrier and end up in the conduction band over here on the p side. Once they get there, because there's a lot of holes on this side compared to the number of electrons, they're very likely to smash into a hole and recombine, eliminating that electron hole pair. So that's this type of passing over the barrier, whether they do it from having a lot of energy and crossing over that way, or by tunneling through, then it's called the recombination current. There's another kind of current which is looking over at these conduction band electrons, or in fact, let's not conduction band. Let's look at the valence band electrons over here on the right-hand side. They're kind of close to the conduction band over here on the left, so maybe we could have an electron move from the right over to the left and just jump through this, tunneling through that barrier, because that generates an electron hole pair in the process. Once the electron's over here, it's not likely to recombine with a hole because there's not very many holes, so that one will stick around. And similarly, creating a hole over here, it's going to stick around too. So that one's called the generation current. Now, the likelihood of an electron having enough energy for it to move from left to right in this majority carrier transport is based on the temperature. So we can use some Maxwellian statistics. You may remember this from a statistical mechanics course. So the current that we get, thinking about all those effects together, the current from this jumping across from having enough energy scales with an exponential given by an energy that depends on the gap energy and the potential applied. You can shift around the relative size of the energy levels by applying a potential, just like we talked about when we were looking at metals, and the temperature. This transport of majority carriers from the left side to the right-hand side is analogous actually to holes transporting from the right-hand side to the left-hand side. So the holes see the opposite in energy barrier. They see that there's an energy barrier for them to jump this way. So to jump down, that's higher energy for holes. So if there's enough thermal energy there, then they may be able to jump from the P side over to the N side. This thermal energy related jumping across is very dependent on the voltage, because it depends on the height of this barrier. All the other conduction mechanisms don't don't depend on the voltage very strongly. So they create kind of a constant current. We'll call it the saturation current, IS. And the voltage dependent one is this first term here. Taking both of them together, it turns out that given that at 0 volts you have 0 current, the PN junction creates a current profile that looks like this. So the forward bias region on the right here, where you apply a voltage to lower that relative energy barrier, means that you can get a lot of current going. So there's a lot of charged carriers here. If we make this barrier low enough, they can just fly right across, and there's very little barrier for conduction. If the voltage is applied in the opposite direction, so that we raise this barrier, then conduction can't take place very easily, because sure, if there were electrons here in the minority carriers, they would be able to jump across, but there's so few minority carriers on each side because of the doping that's not a big contribution to conduction. Similarly, the tunneling effects can still happen, but those are quite a lot smaller than the kind of current you could get in forward bias. Overall, diode behaves like this, gives you a current profile that looks like that. Okay, check your understanding. To forward bias a diode, do you put a positive voltage on the P side or the N side? Take a moment to think about it. So forward bias is what we're going to need to do to put things over into this region, so the positive voltage on this picture. But which side does the positive voltage go on? Let's go back up to the band diagrams. In order to forward bias this diode, we need to raise the energy levels here relative to there. So to raise the electron potential energy, we need to put a negative charge here. That's going to raise this up relative to this side. If we put more positive charge over here, that's going to mean it's a lower potential energy. Electrons would gain kinetic energy by going over to there. So that means we need to put positive on the P side and negative on the N side. That's what forward biasing a diode would do. Looking at the band pictures down here, you can see from these pictures from hyperphysics that in a forward bias diode, we've got the potentials, the battery hooked up so that we put positive on the P side, negative on the N side, and that's pushed the bands closer together. It's easier for electrons to go across. In contrast, reverse biasing the diode means that the gap, the energy barrier, has gotten larger, so it's more difficult for electrons to go across. Another check your understanding. True or false? Above absolute zero and with no applied voltage, the P side of a PN junction is negatively charged, while the N side of a PN junction is positively charged. Okay, think about that. All right, so here's our picture from earlier that we were working with. Here's our N side. It's got all these extra conduction electrons due to the doping, and the P side has all these extra holes due to the doping. Now, you might some of you may be looking at this picture and claiming victory. That's by saying that it was false. So the left side looks like it's more negative and the right side looks like it's more positive. But hold on a moment, because this is just the picture of the charge carriers, so the mobile charges. Actually, the left-hand side is overall neutral, because in order to have all these extra conduction electrons, it has extra protons to go along with all of them. And on the right-hand side, these extra holes come with missing protons relative to the silicon. So both sides by themselves are neutral. Now let's see what happens in the junction. The depletion region here could be where there's some action. So when we have these extra conduction electrons here, they can move around. The extra holes over here can move around. Each side's majority carrier will diffuse a little bit to the other side, and so you'll end up with some of these electrons missing on the left and some of these holes missing on the right. That's going to leave the left side with a positive charge and the right side with a negative charge. So in fact, it was true. One more small section for today, metal semiconductor junctions. This is what happens when we take a metal and then connect it to a semiconductor, kind of combining the last two sections. There's two important types of contact that we're concerned with, a Schottky contact and an ohmic contact. A Schottky contact happens when the Fermi level of the semiconductor is higher than that of the metal. So here's an example where the Fermi level of the semiconductor is a bit above the metal's Fermi level. So when you connect them, then you know that the Fermi levels are going to match up. The way this works out is it's like you kind of fix the points at the junction and then bend the bands around that. So band bending means that we're going to end up with a picture like this. Now, for conduction across this interface, we need to have these electrons over here in the metal be able to jump up to this conduction band there. But now there's this energy barrier because of where the Fermi level was originally. This means that you're going to have some odd non-ohmic behavior across this kind of junction, and this is called a Schottky contact. The other kind you could have is an ohmic contact. This happens when the Fermi level of the semiconductor is below the Fermi level of the metal. Now the band bending happens in the opposite direction, and above the bottom of the conduction band here, you've got a lot of states for the electrons in the metal to jump into, and vice versa. Any conduction band electrons will be able to jump right into the metal because the metal also has all kinds of states. In this region here, there's no energy gap. So the energy gap exists where this Eg is shown. You can't have states in there besides the donor states. But above in this region here, this is the conduction band, and this is all possible states for the metal. So conduction can happen from one side to the other, and it behaves following Ohm's law. Exercise 4.25. Sketch the conduction and valence bands in equilibrium for a junction between two n-doped semiconductors. So this is two n-doped semiconductors, but it's not a homojunction because one of them has a much wider band gap than the other. Okay, so here's what it looks like before. We've got our n-doped. You can tell they're n-doped because we've got this extra little line there indicating the donor energy level, but the one on the right has a much wider band gap. So what's going to happen? The Fermi levels in each of them are going to line up. So that's going to require some band bending. Remember, you fix the spots at the junction itself and then kind of bend them so the Fermi levels line up. This is going to create this sort of an energy picture across the junction. Exercise 4.6. In forward bias, where the generation current is negligible, how much do you need to increase the voltage to increase the current through the diode by a factor of 10 according to relation 449? Assume room temperature. Here is our equation. We're neglecting the generation current. We're neglecting the second term here. So we get that by taking a ratio, a current increase by a factor of 10 requires, after substituting everything in, only a voltage increase of 0.05 volts. Very little voltage to get a massive increase in the current. So in forward bias, a lot of the time you can just say, well, as long as we're forward biased, we've got a fixed drop across the junction of about 0.6 or 0.7 volts. Then around that voltage, you're not going to need much additional voltage to get current, and the diode is behaving like a free pass for current as long as it's trying to go in that direction. You do need some forward bias voltage to make it start conducting, though, because the bands need to be aligned. Exercise 4.8. Draw a schematic of the bands for a metal insulator junction in which the metal has a Fermi level that lies below and above the insulator valence band energy. Metal to insulator junction. All right, so here's the answers for this: before and after, before for the Fermi level that's metal Fermi level above the valence band of the insulator and below the valence band of the insulator. So they're going to line up so that the Fermi levels are aligned. If the metal was above the valence band, we're going to get band bending like this. The bands bend in the same direction for the other insulator metal junction, but we create a different kind of a lineup there that's going on. In either one of the cases, it's going to be difficult. I mean, this insulator, for electrons to conduct in it, they need to jump up to the conduction band. We might be able to get electrons from the valence band to jump into the metal, creating holes with an appropriate applied bias, and then can conduct holes along in the insulator.